we're now ready for Newton's third law of motion, and something, once again, you've probably heard what people talk about. But in this video, I want to make sure that we really understand what Newton is talking about when he says, and this is a translation of the Latin version of it, to every action there is always, and just so you're clear, Newton was English, but he wrote it in Latin because at that point in time, people wrote things in Latin because it was viewed as a more serious language. But anyway, to every action there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. So what Newton is saying is that you can't just have a force acting on some object without that object also having an opposite force acting on the thing that's trying to act on it. And just to make it clear, let's say that we have and we'll talk about these examples in a second. Let's say that I have some type of block right over here, and that I move and I press on the block and I try to push it forward. So this is my hand. This is my hand trying to press on the block and exert a force, a net force in that direction, so that the block moves to the right. Maybe this block is sitting on some type of ice so that it can move. So let's say that I have some that doesn't look like ice. Do it in a more ice-like color. So the block is sitting on maybe some ice like that. So Newton's third law saying, look, I can press on this block, and sure, I'll exert a net force on this block, and that net force will accelerate the block, assuming that I can overcome friction. And if it's on ice, I can do that. But that block is going to exert an equal and opposite force on me. An equal and opposite force on me. And for direct evidence, this is something, even though it might not be so intuitive when it's said, this equal and opposite force, but direct evidence that it's exerting an equal and opposite force is that my hand will get compressed. I could actually feel the block exerting pressure on me. Take your hand right now and push it against your desk or whatever you have nearby, and you are clearly exerting a force on the desk. So let me draw. So let's say I have a desk right here. And if I try to push on the desk, so once again, that's my hand right here, pushing on the desk. If I push on the desk, and I'm actually doing it right now while I record this video, you'll see, so I'm clearly exerting a force on the desk. If I do it hard enough, I might even get the desk to shake or tilt a little bit, and I'm actually doing that right now. But at the same time, you'll see that your hand is getting compressed. The palm of your hand is being pressed down. And that's because the desk is exerting an equal and opposite force on you. If it wasn't, you actually wouldn't even feel it, because you wouldn't even feel the pressure. Your hand would be completely uncompressed. Another example of that. Say you're walking in the beach. Say you're walking on the beach, and you have some sand right here. If you were to step on the sand, so let's say that this is your shoe. Do my best attempt to draw a shoe. So this is the shoe. If you were to step on the sand, clearly you are exerting a force on the sand. You are exerting a force on the sand. The force that you're exerting on the sand is the force of your weight, the gravitational attraction between you and the earth. You are exerting that on the sand. The sand is also, and another evidence of that is that the sand is going to be displaced. You're going to create a footprint. The sand is going to move out of the way because it's being pushed down so hard. So clearly you are exerting a force on the sand. But the sand is also exerting an equal and opposite force on you. Is also exerting an equal and opposite force on you. And what's the evidence of that? Well, if you believe Newton's second law, if you have this gravitational force on you, you should be accelerating downwards unless there is some other force that balances it out. And the force that balances it out is the force that the beach or the sand is exerting on you upwards. And so when you net them out, there's a zero net force on you. And that's why you get to stay there, why you don't start accelerating down towards the center of the earth. Other examples of this, this is maybe the most famous example of Newton's third law, is just how rockets work. When you're in a rocket, either trying to escape the atmosphere or maybe you're in space, there's nothing to push off of, nothing to push off that let you accelerate. So what you do is you keep stuff to push off in your fuel tanks. And when you allow the proper chemical reactions or the proper combustion to take place, what it does is it expels gases at ultra high velocities out the back of your rockets. And each of those particles, you're exerting a force on them, enough force, even though they're super small mass for each of them, they're going at super high velocity, so they're being accelerated tremendously. So there's an equal and opposite force on the rocket, the thing that is actually expelling the gas. And so that's what allows a rocket to accelerate even when there's nothing in this direct vicinity to push off of. It just expels a bunch of things, or it accelerates a bunch of things at a super fast rate. It exerts a force on all these particles, and that allows an equal and opposite force to accelerate the rocket ahead. And another example of this is if you ever find yourself drifting in space, and this is an actual useful example so that you don't end up drifting in space forever. Let's say we don't ever want this to happen. This astronaut, by some chance, he loses his connection to this little tool arm right here on the space shuttle, and he starts drifting away. He starts drifting away. What can that astronaut do to change the direction of his motion so that he drifts back to the space shuttle? Well, you look around, you're like, wow, there's nothing to push off of. He doesn't have any wall to push off of. And let's just assume he doesn't have any rocket jets or anything like that. What could he do? Well, the one thing you could do, and this is the situation, if you're ever drifting in space, is you should find the heaviest, or I should say the most massive thing on you, and we'll explain the difference between mass and weight in a future video. But you should find the most massive thing that you can carry, that you can take off of you, that you can throw, and you should throw it in a direction opposite yourself. So let me put it this way. If I throw, let's say I'm in space and I'm floating. I'll make it look like the glove of a, so let's say that this is the glove of the astronaut. Uh, there you go. That's his hand. That's the astronaut's hand right over here. And let's say he finds some piece of equipment on his, or she finds some piece of equipment on them that they can throw. They can take off of their tool set, and they could find the most massive object that they can throw. So what's going to happen is, for some period of time, while they push this object away, they will be exerting a force on that object. They will be exerting a force on that object for some period of time while they have contact with the object. And that entire time, that object, while it is accelerating, while the astronaut is exerting a force on it, will be exerting an equal and opposite force on the hand of the astronaut, or on the astronaut itself. So the object will accelerate in that direction, and while the astronaut is pushing, the astronaut will accelerate in this direction. So what you do is you throw in the opposite direction, and that'll allow the astronaut to accelerate towards the space shuttle and hopefully grab onto something.